the steps involved in converting an analog or information signal in real world takes through several steps. It goes through sample. We need to sample the analog signal so as to discretize in time domain. Then we need to quantize it. The second step is to discretize in amplitude domain. So the discretization in both time and amplitude will result in digital pulses or digital signal. Then we need to encode it. Encoding, you might have studied in MPMC course where you had ASCII kind of codes for text. It was kind of an encoding format. So similarly, we need to encode those discretized amplitudes both in time and amplitude domain. We need to encode them, and finally, to transmit over the channel, we need to convert those digits or the encoded format bits into analog again using pulse modulation. Sorry. This is known as pulse coded modulation, because these are not simply the amplitudes, but these are the encoded versions of the original information signal, and hence the term pulse code modulation. That would be the next part of our study in this unit. Okay, but we need to do sampling, quantizing, and encoding before we pass it on to pulse modulation. So with that idea behind, we started off with a sampling process. Sampling in sampling is majorly governed by a theorem known as sampling theorem, which resulted in the apt sampling duration or sampling rate required in order to recover the original information signal at the receiver. So as per as the statement, formally it states that any information bearing signal, if it is band limited to 0 to FM hertz, then it can be uniquely determined by the receiver if it is sampled at the uniform intervals of Ts not greater than or less than or equal to 1 over 2 FM. And this is known as uniform sampling theorem. Converting into frequency domain of the left hand side, we can write in terms of the rate, or this is known as Nyquist rate, where the sampling rate should be always greater than or equal to twice of the maximum frequency content in the information signal. This is known as the Nyquist rate, named after the scientist Nyquist. This gives a lower limit or lower bound on the sampling rate. Okay, so we'll also see what happens when Fs is exactly equal to 2 FM, when Fs is less than 2 FM, and of course when Fs is much greater than 2 FM. We'll see all such cases, and we'll also prove ourselves or convince ourselves that this is the desired the rate of sampling. This is proved in several ways. So I had listed different sampling approaches. We had started off with impulse sampling. This is also known as ideal sampling, where the name itself says that we need to take impulse train or train of impulses, and we'll be using frequency convolution property of Fourier transform to understand the mathematical insight of this. So we have information bearing signal. I'll just continue from where I had left off. We have an information bearing signal x of t, which is randomly varying in time, and whose frequency domain representation magnitude of x of f is limited to minus fm to fm, or in other words, we have limiting our information bearing signal to 0 to fm hertz only. Just for the symmetry case, I have just taken from minus fm to 0 as well. Okay, so this convinces ourselves that this is the required information signal which needs to be sampled. Then we will do it, and we'll do the sampling process by utilizing impulses or the train of impulses. The train of impulses will run from 0 to several integer multiples of Ts, and if we try to take Fourier transform of that, since we need to check with the frequency domain approach as well, if I take Fourier transform of x delta of t, we know that by the property of Fourier transform, this is simply another train of impulses separated at integer multiples of fss, with of course with an amplitude of 1 over ts, as we know that the area under a delta function is always a unity. Okay, so with that I'll continue from here with x of t, with the information signal at hand, and with train of impulses with me. All I need to do is do sampling. So this graph represents xs of t, which is your sampled version of the signal, which is obtained by simply multiplying the original information signal with train of impulses. Okay, so what this would result in? This would result in multiplication of these two will result in wherever there is an impulse, it will capture the amplitude of x of t. Say at t is equal to 0, so there is, say somewhere here I have an amplitude, so which will be an impulse. Okay, and from 0 to ts there is no multiplication, the multiplication with a 0, and next interval is at ts. So if I take capture ts amplitude, somewhere here I will have the sample at ts, this is at 0. Okay, at 2 ts I will have another sample somewhere here. At 3 ts somewhere here, and similarly on the negative scale somewhere here I may have the sample at minus ts, and for minus 2 ts, okay, and so on left hand side and as well as on right hand side. So these are all the sampled versions, and hence it is x suffix s of t. It's a sampled version of your original information bearing signal. Okay, we will come to this, how will the Fourier transformation of xs of t will look like, or the frequency domain representation of the sampled version will look like, can be understood by writing few mathematical equations. All we have with us is x delta of t. X delta of t is train of impulses, which I have written already. Say x delta of t is nothing but which is running over minus infinity to infinity delta of t minus nts. This is the impulse train that we have with us. Okay, where ts is the sampling period. Okay, this is the sampling period, and we'll choose this ts to be exactly equal to 1 over 2 fm. Okay, so we know that sampling theorem states that ts should be greater than or equal to 1 over 2 fm. We'll choose exactly the lower bound of it, which is exactly 1 over 2 fm, so that Nyquist criterion is just satisfied. We know that using shifting property of your impulse function, we are aware that from your signal theory that if you multiply x of t, any signal x of t, with time shifted version of an impulse by the property, we know that this is nothing but this is the sample at t naught itself times delta of t minus t naught. Okay, so this is known to us. With using this property, that's what I told, this is this impulse sampling is based on this shifting property. With this we can see that our sampled version of the information bearing signal xs of t is multiplication of x of t times x delta of t, which is nothing but summation minus infinity to infinity x of t, just replacing the definition of x delta of t from this expression, which is nothing but delta of t minus nts. Okay, which is equal to, from shifting property, now I can apply shifting property which I have quoted earlier, which is nothing but x of nts times delta of t minus nts. Okay, this is very evident from the shifting property itself. Okay, now if I want to have frequency domain representation of this, okay, I can since I also have Also we have x delta of f, which is a Fourier transform of impulse function, which I have written in this expression. I will pick the same expression here just for a continuity of the representation, the frequency domain representation of our sampled signal, which is x delta of f is nothing but 1 over Ts summation minus infinity to infinity delta of f minus nfs. Now multiplication of two signals in time domain x of t and x delta of t is convolution in your frequency domain, right? That you have already aware of it. So if I want to find out the frequency domain representation of the sampled version of my information bearing signal, this is nothing but the convolution of x of f and x delta of f, correct? So that I can do the convolution, I can um, uh, perform the convolution, which is by again using the convolution property of an impulse function. This simply gets simplified as x of f minus, since it is okay, I'll just write an intermediate step. This is nothing but x of f convoluted with the summations of several delta functions. If I take in general, this is delta of f minus nfs. This is nothing but x of f minus nfs itself. Again using the convolution, again using the convolution property of delta function. Now we can easily see that x s of f is nothing but okay, x of f convoluted with, in fact I have to convolute with x delta of f here. So this is nothing but convolution with the whole x delta of f, which is 1 over Ts summation, and is minus infinity to infinity delta of f minus nfs. Okay, so if you convolute individual element of this summation, it will result in simply 1 over Ts summation for n is equal to minus infinity to infinity x of f minus nfs, correct? So this is my frequency domain representation of the sampled version of the information bearing signal. So if I want to replicate this on my diagram, as you can see, for n is equal to 0, it is simply x of f itself. Okay, with of course with a reduced amplitude of 1 over Ts. So x of f is nothing but our frequency domain representation of original information signal, right? So for n is equal to 0, it will have x of f. For n is equal to 1, it is x of f minus fs, where x of f is frequency shifted by fs, and so on for all integer multiples of n. And so happens with the negative scale as well. So I can easily represent the frequency domain representation of x of f now, where this is x s of f, which is nothing but 1 over Ts summation and minus infinity to infinity x of f minus nfs. Okay, first I need to write for n is equal to 0, which is x of f itself, which I have already written, which is nothing but which takes the original information signal for n is equal to 0. Okay, pardon me for the not drawing it in actual scale, but next it will be for n is equal to 1, which is a shifted version of this. Say if this is 0, frequency scale, and it will shift for the center frequency to be fs, and hence the same information bearing signal shifted by an amount of fs. So this will be fs, I can say this is the width of your fs plus fm. Okay, I need not specify anything because I'm just shifting this. And next would be the shifting version with a center frequency of 2fs. Similarly, on the negative scale, now this is the waveform that is transmitted over the channel. Just the sake, let's forget there is a block of pulse coded modulation. Let's say just sampled version of these are transmitted over the channel. Now what is the job of receiver? Receiver job is to recover these original information signal out of the sampled version which is received by the receiver. Okay, now what if I just implement just a filter? Where is the information bearing signal? It is exactly sitting at a center frequency as 0. Now if I can apply a filter, say a filter exactly, say I need not have the same amplitude. I'll take the amplitude of this nature. Okay, if I have an low pass filter, this is simply a low pass filter where cutoff frequency is fm. So with this kind of low pass filter, I'll truncate all the higher frequency contained in the received sampled version of the original information signal. If I try to apply filter, which if it is passed through this, then I can recover the frequency. I can recover the original information signal at the output of this filter. But the problem with this kind of approach is, as you can see, no practical filter will have such kind of infinite steep at the rising part and the falling part, where you cannot have straight. No practical filter will give you such high steeping at the rising point and at the dropping point. It will have some falling time and definitely it will have some rising time at its left and right edges. But this is an ideal case where an ideal LPF or low pass filter if you have with you, then definitely you can recover the original information signal. Okay, so this is the case with fs exactly equal to 2fm. So if you consider a practical scenario where if you want to say have a rising and falling time of a filter to be slowly rising, in the sense all the practical filters will have this kind of filter characteristics where they'll have some rise time and sorry, they'll have some rise time and they'll have some fall time. If you apply such kind of filter to this, definitely it may take samples of the adjacent the samples as well. Okay, so that's the reason you may incur some errors in reception. But if you have sampling frequency fs much greater than 2fm, say this is a case with fs exactly equal to or exactly satisfying the Nyquist criteria. This is the case where applying a practical low pass filter may not give you the faithful output of your information bearing signal. If you have a sampling rate, say if you have a sampling rate much greater than 2fm, so I'll take that case. Okay, say for fs exactly equal to 2fm, this is a case with critical sampling. Okay, in case of critical sampling, the problem associated with is the LPF or the filter must be ideal. Okay, so and hence we will not be looking for the exact rate of Nyquist criterion. We will have a rate greater than 2fm, which is the case with oversampling. Okay, you can easily see that in case of oversampling, we can have what would be the scenario at the sampled version of the signal. I'll try to depict that. In case of sampled version, okay, in case of oversampling, xs of f would look something like this. This is the original information bearing signal for n is equal to 0, varying from minus fm to fm. Okay, now somewhere here was my fs, where its left edge was exactly touching the previous version of its sample. Then I just move this next sample little ahead, greater than 2 fm. Then it will have its next sample somewhere here, minus fs. Okay, now if I try to apply a practical filter, okay, which will which if you give relaxation in its rising and falling times, then it will have a kind of this response. Okay, if these are the cutoff frequencies of this low pass filter, if this is a low pass filter, then definitely I will not be taking samples from the adjacent replicas of your original samples at n is equal to 0. Okay, this is how I can avoid any kind of overlapping between the adjacent samples if I try to sample at the rate much greater than 2 fm. Okay, that is one of the important noteworthy point at this stage. Similarly, you can think of what would happen if fs is less than 2 fm. So this is the case with undersampling. There's a case with undersampling. So what will happen with undersampling is, can anybody guess what will happen with undersampling? Yeah, any answers I have?
Signal won't be reproduced faithfully.
Faithfully, do you think so?
Overlapping of the band.
Exactly. There will be definitely overlappings. Yeah. So if this is F, if this is my original information bearing signal, minus FM to FM. Okay. Now this Fs is less than twice of FM. So definitely I will have somewhere here as my sampling frequency. So the replicas will try to overlap with one another. Okay, similarly that will happen in case of the negative scale as well. Okay. This would be, pardon me for all these non-scaling versions of this, but still I try to depict what is 2fs and so on. Okay, this would be 2fs. As you can see, there is a clear overlapping in this region where it tries to crosstalk with its adjacent sample. And even if you have an ideal filter which has infinite rise and infinite fall, you'll not be able to recover the original signal back. So the overall structure of this would be somewhere like this, right? So since there is an overlap, this is your recovered signal. If you try to get back the original signal, even with the case of ideal sampling, sorry, ideal filter, okay, which doesn't definitely represent your original information bearing signal. Okay, this kind of effect which has an overlap, okay, which has overlap with adjacent replicas, okay, is termed as aliasing. Okay, this is the technical term or technical jargon which is used in communication theory. Our job is to negate this aliasing effect. I'll talk about I'll take some 5 to 10 minutes to talk about aliasing in next session and how to overcome if there is an aliasing. Of course, you may be sitting comfortably and thinking that to avoid aliasing, all I need to do is simply oversample it or keep my sampling rate much greater than 2 FM. Remember, I try to give you the practical scenario where no information bearing signal will be strictly band limited between -FM to FM or A0 to FM to be strict sense. So no information bearing signal, okay, say practically in reality you will not get, okay, no information signal or information bearing signal is strictly band limited. Okay, keep this in mind. Okay, each of those, every information bearing signal will have like this originally. Of course, we have taken it varies between 0 to FM. Okay, but in reality they will have their own tails. Even if you sample at a high frequency rate, there is a chance of these tails cross talking with their adjacent samples. Okay, in spite of keeping fs much greater than 2 FM, still you may incur aliasing. Okay, to avoid such practical scenarios, we will make use of a filter called as anti-aliasing filter. I'll talk about that when I take a little more detail about aliasing. Okay, the anti-aliasing filter job is to simply truncate the information bearing signal to FM. Okay, it first band limits the original information signal. We assume that any information bearing signal which is greater than FM will have least amount of information in it. Okay, the first job is to truncate this signal to make it band limited between 0 and FM. Then you apply to sampling, then you can do other jobs. Okay, but please make sure that although the filter the one limitation would be with respect to the filter characteristic to recover waveform from sample data, where they cannot have infinite rise and falling time, and that's the reason we go for oversampling. In other words, or in other cases, alternatively, the information bearing signals themselves in reality will not be band limited. Okay, so that would be the two reasons for which we go for more, sampling rate much greater than the critical sampling, which is 2 FM. Okay, any questions before me on to next type of sampling, which is natural sampling. So this in turn proves our Nyquist theorem or Nyquist rate, where we should keep Fs much greater than 2 FM. Okay, that's what we are trying to do. Since we stated Nyquist theorem in words, our job is to prove that theorem in several with several cases. First, I started with ideal sampling. Then I'll move on to the more practical sampling type, which is natural sampling. Okay. Yeah. Next is with respect to natural sampling. Here we try to demonstrate the validity of the sampling theorem again using the frequency shifting property of the Fourier transform. Okay, so earlier we used convolution property of the Fourier transform to prove the sampling theorem. We will use frequency shifting property of the Fourier transform in this case. So we will use frequency shifting property of Fourier transform. Okay, although instantaneous sampling is a convenient model, in the earlier case we took impulses or train of impulses in earlier model. A more practical way of accomplishing the sampling of a band limited analog signal x of t is to multiply that analog signal x of t, which we have taken earlier, by the pulse train, which will have a finite duration of time interval. Or if I pick the same diagram which I taken earlier, okay, these will remain as it is. I'll pick that here again. Sorry, give me some time. Okay, so I have picked the same information bearing signal, but instead of impulse train, now I will take pulses. Okay, how do those pulses look like? Okay, I'll have frequency domain representation of those pulses as well, so that I can apply filters and understand the characteristics of the filter, what they must be in order to get the original information signal back. So the only difference here is now it's a more of a natural thing. I'll take the pulses now. It is not the impulses. These are of pulses of finite duration. If this is 0, these are all pulses. Okay, so this is of a more natural thing, where if you want to apply as switch using any transistor, the switch is turned on for a finite duration of time in order to capture the sample of your original information signal, and this will mimic close to that. So this is your TS, this is your 2TS, and so on. This is your minus TS, minus 2TS, and so on. Okay, so this is your XP of T, which represents the pulse train. As you know, the Fourier series representation of this is minus infinity to infinity. Since it's a symmetry, you will not have an and bn terms. There will only be a cn term, which is represents the function that I have taken is symmetry, even symmetry. So cn e power j 2 pi n 2 pi n n fs t, where fs is the sampling rate. Again, with respect to the sampling rate, we'll keep the same sampling rate like earlier. We'll take the critical sampling rate, which where fs is exactly equal to twice of fm. Okay, we'll take with that critical sampling, then we can oversample in order to take those spectrums farther apart. We'll just see how will the frequency domain representation of the pulse, the sampled versions of original information signal. Okay, so this is the Fourier series, and similarly I can represent the frequency domain representation of this xp of t as xp of f. Okay, first I'll write all these expectations. Okay, again what we are trying to do here is we are trying to multiply this in order to get the sampled version of the information bearing signal. We are trying to get x of t multiplying with x p of t, okay, with the natural sampling, where this xp of t can be represented using Fourier series, which I have written already, minus infinity to infinity cn e power j 2 pi n fst. Okay, then if I try to take Fourier transform of this xp of t to represent in its frequency domain representation, where cn, this also you should know that these are the coefficients. Cn is obtained by integral over minus infinity to infinity xp of t e power j 2 pi nfst. Okay, and this is, it will not run from minus infinity to infinity because we have taken one duration of xp of t, which will last for a finite duration of on period. If I take the t as its period, as on time, okay, then I can write this as Cn as 1 over Ts. By integrating that, you'll have integration over e power minus j2 pi nfst, and this will have unit amplitude for only t duration of time, and integration of e power minus j theta. If you try to integrate over t, that will give you e power minus j2 pi nfs itself over minus j2 pi nfs. And you know that with a complex representation, complex form of representation of sinusoidal function using your Euler's identity, you will have sine theta over, sine n theta over n theta, which is represented as a sink. I'm just not writing those the formal steps. I'm just looking for the final expression of this, which you can, of course, find out on your own. Where this sinc y, as you may have already know, this is represented as sine pi y or pi y. Okay, and how does this sinc function looks like? You can draw the sinc function. We know the amplitude of the sinc function, which will have infinite tail. Its major lobe looks like sine. It will have lower values, and it will keep on diminishing in its value on both left and right. Okay, that's how your sinc in a function looks like. We'll limit ourselves with a major lobe, where majority of the samples will be can be considered within the major lobe itself. So if you try to take that, I can represent x s of t as x of t multiply with xp of t. I have come back to this equation now. Minus infinity to infinity Cn e power j 2 pi n fst. Okay, now if I apply Fourier transform on both the sides, okay, this is Fourier transform of the whole product x of t summation minus infinity to infinity Cn e power j 2 pi n fst. Okay, and we know that Fourier transform and summation are the linear operators, so we can exchange or interchange the operations of the summation and Fourier transformation, and hence we can write this excess of f as simply as taking summation outside minus infinity to infinity. Okay, and Cn is also a constant. I can take Cn out, and this will be simply Fourier transformation of x of t e power j 2 pi n st. Okay, now you know the frequency shifting property of your Fourier transform, where when it gets multiplied with exponential of something with respect to the signal x of t. Now using Fourier translation property, these are the fundamentals of your signal theory, and there's a reason I'm just going little faster. Translation property. In fact, this is Fourier frequency translation. Frequency translation property. Using this, I can write xs of f as simply as summation n minus infinity to infinity Cn. Simply, it will take x of, this is nothing but x of f, but all shifted version of NFS. It looks exactly similar to our ideal sampling case, but only difference is in their amplitudes, because Cn is nothing but, as I had written earlier, Cn has an amplitude of 1 over Ts, sinc of nt over Ts. We know that sinc function will have amplitude, it's basically, it will have a function of since Cn is function of sinc mathematical relation, so sinc has a major amplitude in its region of 1 over minus 1 over t to plus 1 over t, and it has diminishing amplitudes beyond that points, and hence the frequency domain representation of my sampled version will accordingly vary. If I try to write now, what will happen? Xp of f that we know is actually depends on the coefficient Cn, which I've written there. This will also have, I mean, this will have its major lobe as sinc function. Okay, and so on the negative scale. I'm just looking for the major lobe here. So C naught will have this value. So this is your C naught. Okay, somewhere at Fs, since you have taken Fs, somewhere you will have C1. You have taken 2Fs, somewhere you will have C2. And similarly with the negative scale, if this is minus Fs, here this is C minus 1, and similarly at minus 2Fs, and so on. Okay, and now I'm multiplying x of t with xp of t, so I need to represent the time domain and frequency domain representation of sampled versions of these. Then it will be evident why it is called as a natural sampling. Okay, any questions meanwhile you can ask. It's okay.
So that dotted line is not going to be there, right? It's just like
yeah, which one? These dotted lines?
on for XP of f.
Yeah,
so the
XP
dotted
of
line
f.
is not.
Dotted line will not be there. I'm just have represented that this amplitudes of these impulses will be if you try to connect them virtually, it will represent the sinc function which exists in the major lobe. Okay.
Okay, so understood.
Yeah, so this is the sinc version which I have written. I have just to make sure that this is the coefficients which are derived out. I mean, these amplitudes are derived from that sinc function. Just to ensure that I have just written these dotted lines. Okay, there will not be any samples in between 0 and fs or fs and 2fs. These are the amplitudes which are the coefficients which take virtually take the amplitudes of the sinc function itself. Okay, so if okay. If I try to plot this sample version in both in time and frequency domain, how does it look? Okay, just give me a minute so that I'll try to draw. Okay, so if I try to draw this, then how does it look at this sample at t is equal to 0? So okay, when you multiply, this is your xs of t now. This xs of t is multiplication of x of t and xp of t. Okay, now you are multiplying these two signals. Then if you try to see that at t is equal to 0, it is at t is equal to 0, what is a sample of this x of t will exactly appear here. Okay, so this is a sample version of it at t is equal to 0. Okay, this in the time domain. Then for the next time interval ts, it takes the sample of this original information bearing signal. So I should take exactly same of this. Okay, this is kind of a rising part which it is capturing. Okay, so kind of this kind of amplitude for ts. Okay, this is not flat in fact. So at t is equal to 0, there's something like small rising kind of curve which will be the effect of the natural sampling. Then for 2 times ts, somewhere here if I take, it will represent that curve. Similarly, for minus TS, it will have something like this. And for 2TS, it has kind of this waveform, and so on. And hence, it's a natural sampling where the amplitude of these pulses, unlike in the case with impulse sampling, are not instantaneous values. These are all for the finite durations. So for the finite duration, how your original information bearing signal is varying, that is reflected on their amplitudes as well. So it is a natural amplitudes of your information bearing signal, and hence the term natural sampling. Okay, so that's the straight away difference between your impulse sampling and natural sampling. Similarly, if I want to represent on the frequency domain part, xs of f would be what? The at f is equal to 0, at f is equal to 0, definitely it will have the similar property of your band limited signal at f is equal to 0. Okay, so this is varying between minus fm to fm. Then next part is C1 times xff minus fs. As you can see, we have derived an expression of xs of f. It is C1 times x of f minus fs. So I need to multiply this shifted version of x of f by an amount of fs and multiply its amplitude by the coefficient C1. So I need to look for the amplitude of C1 and try to shift this the sampled version. So next would be kind of this, where this is fs whose amplitude is C0. Here the amplitude is C1, and similarly at 2fs this is amplitude is C2, and on the negative scale we'll also have similar structure, minus C1, and this is represented with minus C2, and this is at minus 2fs, and so on. Okay, again, so if I try to virtually connect these amplitudes, it should look like major lobe of your sinc function. Okay, I'm sorry for not drawing to the scale of natural sampling. If you try to compare, if you try to say what is the similarity between ideal sampling and natural sampling, both are same only in the limiting case, where if I try to take this TS, say as TS tends to 0, okay, if I limit the value of TS tending to 0, this is nothing but your impulse sampling. Okay, this is nothing but impulse sampling, where all your coefficients Cn's where will turn to be a constant amplitude. Here all the Cn's were decreasing or governed by the sinc function. In case of TS limiting to 0, Cn will all Cn's will have constant amplitude of the amplitude of 1 over Ts, as it is evident from this expression itself, where I have written Cn is equal to 1 over Ts sinc of Nt by Nts. So as Ts tends to 0, this is a form of sine theta by theta which tends to 1, and hence all irrespective of value of n, you will have a constant amplitude of 1 over Ts, and hence both ideal sampling and natural sampling are identical to each other only in the limiting case of Ts tending to 0. Okay, so in both the case, your fs, this is a case with fs equal to 2fm for the critical sampling, for the exact sampling, and if you have undersampling, again there will be overlapping or aliasing, and if you have an oversampling, then definitely you can pull these adjacent samples apart from each other such that you can recover your original information bearing signal. So the same theorem holds good in case of natural sampling as well. Okay.